All right, little intro to what's going to happen in this this set of problems here that we've got. That's basically just trying to get you ready to actually find a volume. So I broke this out and made it so that we can just go down through these shapes and problems that are down here and talk about what the capital B stands for in these formulas first of all, and then basically just finding dimensions of these things when they might be a little weird or just in a weird way. So first of all, I'm going to zoom in on these formulas. We have a capital B right here and a capital B right here. That is incredibly important. And as it says right here, any formula with a B in it, the B stands for area of the base. And the reason this is important, B, area of the base. It is a shape. In a lot of our formulas that we've used, we have a little b, which means base. That is a side. Okay, those are two very different things, a side and a shape. So it's going to be important not to mix those letters up when we're writing the formula down and when we're actually doing them. I always remember that for this one right here, for the capital B, you need two dimensions. Okay, because in order to get an area, you need like length times width or base times height or 1/2 base times height or something else. So you need two dimensions unless they explicitly give you the area of the base, which they may do. So just think about that. It has to be an area, so it has to be a shape. So there's that first most important part. Then this sentence right here. So it says, the way that 3D shapes are, the base is not always going to be the bottom. And I know that we've talked about this with triangles before. We have the ability to turn things, to turn pictures on their side and make different things sit on the actual quote unquote bottom of the shape. So it doesn't have to be the bottom. This is what we're going to do for the rule here, for any prism. And I said this in, if you did some of the last assignment, if you watched some of the videos there, this may have been talked about in the one that you watched. There has to be two of these shapes to be the top and the bottom. They have to be identical, congruent, exactly the same. They also have to be parallel so that they can't touch each other. So when we go down through these problems and these example problems, I'll talk about and I'll highlight things and show you where they are. But that's the way to think about it. If you think of a box that comes to your house with something in it, it has a top and a bottom, and the top and the bottom are exactly the same. You can open up the top, you can open up the bottom. Whatever you do there, they're exactly the same, and they sit, one sits on the floor, one sits up in the air when you have the box sitting there. That's for prisms only, all right? Only for prisms, all right? For prisms. Sometimes it doesn't matter what the top and bottom is. You might be able to turn that box different ways and open other parts of it. So we've really got to be able to think about this. This is probably the hardest thing of any of these volume formulas that we have to deal with, the prism bases, because they are all different. And you're going to see lots of examples in this file and also when you take the Schoology quiz. For pyramids, which is the other thing that has the B in it, it's real simple. Okay, I highlighted too much there. The prism is opposite from the apex, the base. All right, so the apex is the top point that we talked about. The base is going to be a square or a rectangle or any number of other shapes, but it's the opposite side from the apex. Very straightforward. You'll also see some problems in here that are going to talk about this. Okay, the height. So the height of a three-dimensional shape sometimes is confusing. Oftentimes it's not. For cylinders and cones and pyramids, I don't think it's confusing where the height is, but for prisms, it might be. So for a prism, it's the distance between the two bases. And I'll show you this when I do some problems. You have to think of that box. If it's not sitting on its base as the bottom, you have to think about it turning. And how far would it stand up if it was actually sitting with its bottom placed on the ground? Because again, I've said this in the videos in the last assignment, and then there'd be some in this one. If we don't have the dimensions in the right spots, we cannot get these problems right. And we get the formulas. It's one of the only things we get the formulas for in geometry, so we don't want to miss this stuff. So please pay attention to these. Maybe do a couple extra examples than you would normally do, because we've got to know what these things are, or we're just going to be frustrated with this and not be able to do it. And it's such a nice thing to have in a test or something, because we get the formulas.